Hi, my name is Armando Diaz, and I'm going to be presenting a paper called An Evaluation of Open Source Serverless Computing Frameworks Support at the Edge. So the content for this presentation is divided in three sections. The introduction, which I will be just talking about some terminology used during the paper. Also the body, we just talk about the requirements, methodology, evaluation metrics, which is divided in two main points, which is qualitative and quantitative metrics, and finally the results of these metrics. Also, of course, the conclusion. The introduction and IoT devices. New technologies are coming out, such as self-driving, smart cities, augmented reality. All of these technologies are in constant interaction with our IoT devices. So they require real-time data processing, which means that they will be just pushing data, but also like receiving uh, data in real time. So this data needs to be processed, it needs to be clean, needs to be transformed and used to operate other devices, or also to send that data to just be analyzed and make or perform like decisions in real time. So that means that we need an architecture that can be low latency mainly. So a solution for this is it's an architecture called edge computing, and here in the picture we can see two main components, which is a data center. For the data center, just means that you own the servers. That's like the main thing there. You are the owner of the servers. You have some benefits, of course, because you can have like uh, high performance and low latency, but also it can be very expensive, right? I mean, you need to worry about the maintenance and also the servers. Of course, they don't last forever. You have the cloud computing too. So in this side, you can pay on demand. You can reserve also just instant instances. Something very interesting here is that there is a intermediate component called edge. These are also called edge locations. Um, that means that these are located in a very is in a strategic way, and just to be close with the end users, provide low latency, of course, like high performance. Also, locations have a cache, a buffer, just some optimizations to communicate with other devices in a fast way. Now we have stateless applications. The paper talks about Kubernetes, and there are two main applications here, which are like stateless application and stateful application. But we're gonna focus on stateless, because here the concept of this is that we don't need to the application doesn't need to just remember information, like it doesn't have to store information basically. So this makes things easier, because you don't worry about storing information, but also it's just simpler. You can just create, you can have like multiple servers. Maybe one of them can just shut down, and it doesn't matter, like you don't have to be concerned about the communication that was between your application and the server, because just the application can go to find a different server, and you send the like a token to authenticate that you have the just permissions to send data and also to request data. uh, Here, serverless architecture. For serverless, this is this the server the traditional the tradition let's talk about first about the traditional architecture. For this part, that means that you are basically stuck with the capacity that you have in your servers, that you need your servers to be like up and running like all the time. That 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 means that your system will be like, or it can be very very expensive. But the serverless is using a client side, as it says here. And serverless doesn't doesn't have a server or a computer that is that you are worry or just pain all the time. Like there can be a lot of events or that can trigger a serverless application. This can be like such as like you can have like maybe a website, and in this website you click or sign up or buy an item, and that item will trigger a different application just to confirm in the backend side logic that you have bought a product, for example. So that trigger doesn't have a server in the other side that is just like running all the time. It just like trigger events, or is triggered by events. This is just the main thing about serverless. Um, of course, you need to worry about security, and you might have a database too. Um, but all of these things can be carried out by other applications too. For the body, just the requirements of this paper. We need low latency, we need a high availability, and also we need privacy. So one of the reasons why the the authors wanted to study open source frameworks is because um, cloud computing, like such as AWS or Azure or Google Cloud, like it doesn't matter the name. These some of these services that they provide can be uh, they can they can be very difficult for the user to not rely on them once they have started working with them. So that means that they they need just a solution, or like a framework like open source that can be used in multiple vendors. Like it doesn't matter if it is AWS, it doesn't matter if it's Azure. We just need a framework that where you can launch your application, and you can just perform any operation or functionality to your users, and you just have your products up and running. And so one of the frame the study, the paper analyzed the first four frameworks that are here in this picture, which is like Apache OpenWhisk, Knative, Open FAAS, and Kubeless. Here we have the number of contributors that are associated to these frameworks. And as we can see, just the authors chose the top four frameworks related to orchestrating and also managing resources to have low latency with these requirements. Um, they perform an experimental architecture, which is this is in this picture. As we can see, we have two main layers, which is the edge computing layer, but also we have an IoT device layer. For this, the first one, this one is divided also into two sub layers. The first one is the physical layer, where it has just the servers or the compute. This one, each server has a Docker image, which has the operating system and also the applications that will be running or executed. The first server corresponds to the master node, and the second one to the worker node in the Kubernetes layer. And we in this part we have also the, well, under the IoT devices, um, we have more servers, but these are these are Raspberry IoT devices, sorry, and these have installed a JMeter, which will be uh, monitoring metrics and also uh, just receiving responses and requests, HTTP requests and responses. So this is just the experimental or the experiment that the authors did. The metrics that they gather, they are divided by framework. So for example, we have here the kubeless. They analyze if the framework was open source, or which type of license was associated uh, to this framework. Also, all the programming languages that were supported, container orchestration engine support, if it was Kubernetes or it was something different. Also, the monitoring supports. Here is Prometheus and Grafana. Also, function triggers, if it's HTTP or other types like event sources. Auto scaling, if it has auto scaling or not, and also well, if it has SLI command line interface. And finally, the ease of deployment. If the deployment, I don't know, the duration is like, in this case is 5 minutes, but for other cases like Apache OpenWhisk is 15 minutes. For the OpenF AAS is 10 minutes. So the main difference between all of this is the ease of deployment. The 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 one that is performing better, according to these qualitative metrics, is kubeless, as we can see. And also we have the mean response time. So these are just more quantitative metrics. For the mean response time, we can see that kubeless is the one that has very low response time, which is pretty good. This is pretty good. And here we can see it says one service, and here 5 services, but they tested the concurrency in the with the same frameworks. So in the first one, we just have like one service. In the second one, we have 5, and they measure the same thing, just to see if you increase the the concurrency, if the response time will change or not. So for the Apache OpenWhisk, this one did decrease when you add more concurrency. For the output, which is how many transactions are per second, we can see here that these three are almost the same. Almost the same for 1, 5, and almost the same for 10, 15, and 20. So and the worst one is Apache. So this one is the worst performance. And success rate, this one is just measuring how many requests uh, performed well, uh, divided by all the requests that were sent. So the same here. When it's one service, Apache is very similar to the other frameworks, but when we have like more concurrency, it performs like very, very badly. And for just the conclusions, as I already mentioned, uh, just the main points. We want to reduce processing time. Uh, just the best performance was kubeless, and the worst performance was Apache OpenWhisk. And some challenges that need to be studied in the future is just the uh, observability, resource limitations, and fault tolerance. These are the references, and that's all.